Welcome again to the Windows Performance Deep Dive channel. In this video, we deep dive into exposing CPU and thread activity and inactivity on your Windows device. One way that ETW captures thread activity is through sampling. Every millisecond, the operating system checks every running thread, that is, every logical CPU, logging its execution address in the code. Also with each sample, ETW can capture a stack walk, which is the execution path of function calls that led up to the currently running code. These stack walks, also called call stacks, are later accumulated in the Windows Performance Analyzer, WPA, to form a call tree. The branches of the call tree with the most samples represent the most active code. Here we have a screenshot of WPA analyzing a CPU sampling trace. In this view, the various colors represent different running processes. We'll focus on green, which is the Excel process, with a particularly active thread. This thread's thread proc function is called winmain_crt startup, contained in the excel.exe module. The stack column goes from winmain to main loop to fdoidle and so on, to execute a save operation for auto-recover. Nearly 70,000 samples in the count column at about 1 millisecond each amounts to nearly 70 seconds of CPU time doing the save. Here's another view of the same trace, which has no stack column. So this time we're focusing on the functions where the samples were actually captured. We can quickly see that this thread spent about 49 CPU seconds in an 80-second trace, executing code within the MSO-Win32 client module. And most of that was in a function called deflate, which itself spent 27 seconds doing data compression. We'll come back to this trace later. Another way that ETW captures thread activity and inactivity is by logging thread transitions. This chart represents two threads. The top thread experiences 5 transitions. It's initially running, but then it blocks as it perhaps waits to enter a critical section, or it waits for disk I/O to complete, etc. Once it's signaled or released from the wait, it enters the ready state, and then eventually it's scheduled to run by the OS on one of the logical CPUs. Now recall that every CPU core on the device hosts one logical CPU, or 2 logical CPUs if hyperthreading is enabled. After a while, the thread hits its 4th transition, where it is preempted and drops back to the ready state, because there are other threads that need to run, but not enough logical CPUs to run them all simultaneously. And finally, our thread is again scheduled on a CPU to finish the trace. That top thread is called the new thread, as it transitions from waiting to ready to running. That's what makes it new. The bottom thread is the ready or readying thread. It's the thread that puts the new thread into the ready state via a signal release, like set event, leave critical section, etc. Every one of these thread events logs a timestamp, and 2 of these events also do a stack walk. The readying thread gets a stack walk when it does the signal release. The new thread gets a stack walk when it gets switched in and scheduled to run. This stack walk captures the execution stack at which it was switched out. To boil it all down, we have 3 types of events happening across 2 threads. First, what we're calling the new thread gets switched out. It is waiting on something, or perhaps it was preempted and taken off the CPU. Then, in the case where it's waiting on something, a readying thread issues a signal and logs a stack walk as it releases the new thread. Then finally, the new thread logs a stack walk as it is rescheduled, assigned to a CPU, and switched back into the running state. Here's another view of that same trace as before, but this time it's viewing the thread transitions. This is effectively that same call tree where Excel is saving the file for auto-recover. Let's go through what the columns tell us. The waits sum column shows the sum time spent waiting, 184.8 milliseconds, not very much. The count of waits shows that there were 574 individual wait periods that make up those 184.8 milliseconds of waiting. The wait's max column shows that the length of the largest individual wait was just 7.36 milliseconds. The ready sum column shows how much time was spent ready to run, but not actually running, 9,533 milliseconds. So the main thread is experiencing CPU contention. It is being crowded out by other background threads for 9.5 seconds. Then the ready max column says that the largest individual period of ready but not running was 408 milliseconds. And finally, the CPU usage column says that the thread was actually running for 72,101 milliseconds in the context of this trace. We'll see this trace again soon. The script for tracing CPU and thread activity is called TraceCPU, and the standard commands are start, stop, view, cancel, and status, or -- for help. This is a PowerShell script. If your device restricts PowerShell scripts, you can usually get it to work by running the corresponding batch script, tracecpu.bat. See the frequently asked questions in the wiki for other options. The default collection mode for TraceCPU with no switches is CPU samples and thread switch activity with stack walks. That's quite a bit of data logging, so you wouldn't collect in this mode for longer than a minute or two. The start command has these 4 optional switches to reduce what data gets logged. You'd use the -hang switch when your application is hung or deadlocked to see where each thread is waiting. There are also switches specifically for C# code, which is -clr, and for JavaScript, which is -js. Okay, let's do a demonstration. There's a fascinating YouTube channel called Spreadsheets Are All You Need, and they've implemented an early AI system called GPT-2 in an Excel spreadsheet. Unfortunately, from time to time, they'd experience a hang or a lockup and have to wait patiently until it passed. With MSO-Scripts, we can quickly capture a CPU trace of that very scenario, and with any luck, get an idea of what feature we need to disable to stop the hangs or lockups. So we've downloaded the MSO-Scripts toolset, and we've loaded the Spreadsheets Are All You Need document into Excel. We capture the trace with start and stop, then give the view command, and WPA, the Windows Performance Analyzer, opens. Here in this view of CPU samples, we see that Excel, here the orange band, consumes nearly 70 seconds of CPU time in this 80-second trace. We've got a list of thread procs of running threads, and the active one is the main thread, whose thread proc is winMainCRT startup. So we expand its call stack, and we immediately see what code is involved. Main loop is the UI message dispatcher, and fdoidle invokes short tasks to do while it's waiting for the next message. Some short tasks are best done on the main thread for synchronization purposes. One of those short tasks periodically saves the file for auto-recover purposes. But here, it's not a short task. When the file is large, saving can take quite a while, and the user interface won't become responsive until it's done. This is arguably a flaw in the auto-recover feature. Drilling down into the call tree, we see the guts of the save operation and get an idea of which parts are the most expensive. Scrolling down to a different view on the same tab in WPA, there's no stat column with a call tree, so now we're looking only at functions where code was executing, organized by process, module, and function. If we've got full debug symbols, then we'll also see the source file and the line number. Here we see that the most active module was MSO-20 Win32 client, and its most CPU-intensive function was called deflate for data compression. Anyway, now we know that we can avoid one type of lockup on this large file by turning off the auto-recover option, though I admit I'm not convinced that this is the same issue that the Spreadsheets Are All You Need team was experiencing. So now that we've exposed the CPU activity, we want to find out how much the auto-recover save task was slowed by CPU inactivity and why. Here we're back at that first view of CPU sampling with Excel in orange. We right-click on Excel and filter to selection. Now we see Excel consuming about 1/4, 25% of the available processing power, which makes sense as there are 4 logical CPUs, and Excel in this trace is using just one thread to do the save for auto-recover. But there are some gaps in that execution. Let's see what we can find out about that by switching over to the Weight Analysis tab. The first thing to do here is filter to just the thread of interest, the WinMain CRT startup thread, which we'll find in the excel.exe module. We expand the New Thread Stack column, and we see the same call tree, saving for auto-recover. Scrolling over, we've already learned the meanings of some of these data columns. This thread was blocked or waited 574 times for a total of 184.8 milliseconds, the largest waiting period being just 7.36 milliseconds. After the count waits column, that next count column represents all switch-out events. The difference between those two columns then gives the number of times preempted, so the thread was preempted more than 60,000 times in this 80-second trace. The new thread spent 9,533 milliseconds ready to be scheduled onto a CPU, with the largest of these ready periods at 408 milliseconds. Using the right arrow key to expand the topmost branch of the call tree, we will see that at one point, saving was very briefly interrupted by the save indicator on the status bar, checking for an abort message. Finally, in the Ready Thread Stack column, we see the set event call, which released the new thread, which in this case is the main thread, to continue with the save operation. I hope you found this a useful introduction. You could find MSO-Scripts at github.com/Microsoft/MSO-Scripts. Do try it out and let us know what you find.